Okay, everybody excited to listen a little bit to Martin about architecture and what you can achieve with a good and nice architecture? That sounds better. Anyone is in a big project? Anyone had a project with bad architecture that failed? Yeah, you're right. Today Martin will solve your problems. Give him a warm welcome, please.
Yes, I will solve every single one of your problems. You don't have to do anything in the end. The original title I gave was Making Your App Testable, Cloud-Agnostic, and All-Around Awesome with Clean Architecture. As I already said this morning, testable and cloud-agnostic and all-around awesome are just motivators, and don't let yourself be scared off because of the cloud-agnostic part. You can use the same ideas in the front end. So, where applicable, cloud-agnostic. But for the remainder of this talk, I will go and make this with some serverless examples. So, but I hope you can see in the end that you can use the front end with a monolith in the end if you want to. But yeah, just some words about me. I'm Martin. I'm head of software engineering at Junge Haie. I'm doing this programming stuff since I was 6, and that is 32 years ago. I do some form of architecture of software the last 10, and in between I was a researcher and researched parallel distributed systems, cryptography, and autonomous driving cars. So the guys downstairs with the model of the cars have a slight problem because I ask hard questions and they can't answer them. So I'm actually a recovering academic, which will lead into something later on, because academics have a tendency to look at something you would say is historic, because most of the ideas I'm presenting today are 30 years old in research. So you ignored 30 years of tradition and good uses, and so yeah. Okay, usually at this point I do some form of serverless pitch. I hope everybody of you is well aware what serverless is, but I have to do a little bit. What is a serverless application? Usually that means you have no server to maintain. You have some form of flexible auto-scaling. You have automatic high availability usually, and spare capacity is usually handled for you, so you don't pay for what you don't use. You just pay for what you use. But that makes some of the things harder. For example, testing. Everybody knows the testing pyramid, I hope. So in the usual software project, you have a huge number of unit tests, then you have some integration and component tests, then you have some end-to-end tests. They get more expensive the farther up the ladder you go, and then you have manual tests, which are usually very, 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 very expensive, and you want to usually minimize the amount of those. And since we are in the serverless world, and since we are actually doing micro or nano services, depending on who you ask, you usually, in this case, have something more like the testing tower, testing honeycomb. Depending on who you ask, unit tests get less important, or they have the same importance, but what you have is you have more components which are interacting with each other, and so you have to test this integration and components more. So those are definitely getting more important. But when we are in a serverless world, we have the problem that most of our components are provided by some vendor, for example, Amazon or Azure or Microsoft with Azure or Google, and basically we're just the cables between those services. with a serverless application. That's not completely true, but there's some sense to that. And then we have this problem. Usually someone is asking us, yes, but what if something happens? Usually some stakeholder is coming and saying, vendor login! What if Amazon raises the prices, doubles the prices, or switches off everything? To be fair, Amazon has lowered the prices 16 times in the last 5 years and never raised them. But that is something you will always hear. And then we want to, I have this all-around awesome part. Usually another problem is maintainability. Your services evolve, and the more they evolve, the more code you put in some place at some axis somewhere in your code, and then you have the problem of the maintainability goes down every time you do that, because when you're not have no concept of where to add that and where to or if what you have to change or what you have to sorry, then you do it at some point in your code. And if you have a 400-line controller method or something, and then you put 4 more lines in there, the maintainability goes down. And then the next stakeholder comes around and asks you something, and you have to do the same thing, and so on and so on and so on. And minutes later, or requirements later, the method is 500 lines long. And then at some point, cargo cult starts, and you say, "Oh, we can't take. Nobody knows anymore why this part is in here. We can't change it." Maybe you can, and you can maybe even make it very much simpler, but nobody knows anymore. And you keep it in that code, and for the rest of eternity it's in your code. And nobody knows why. So, one idea to counteract that is clean architecture. Clean architecture is one architecture concept. Everybody knows software architecture, I presume, but I will say some few words about it. Usually, software architecture there are two kinds of software architecture that are described. One is, yes, we have a DynamoDB, and we have this component and that component and that component, and all those are stuck together like this, and then there are arrows between them. I see the software architecture the other way around. I say, okay, I have some business logic, some use case, something I want to achieve, and then I would like to program that, and then I would like to make the decision what component goes in which position very much at the end. And I want to give my programmers the ability to write the business logic out without knowing which components are in the end used to store data, to compute something, to present that to the user, whatever. That should come at the end. That is, as I said, something which is 30 years old. 30 years ago, DCI, which is short for Data Context Interaction, was introduced. The same person who introduced this was also the same person who introduced MVC. Wrote a large part of the UML specification. His first software project, CAD/CAM, was written in 1963 and is something like LaTeX or TeX, where there are very few changes till the mid-90s, and it was used as a CAD program in shipping yards for until the mid-90s. So he knows what he's doing. Basically, around the same time BCE was introduced, These two don't reference each other because they are basically at the same, developed at the same time. I tried to find out what BCE means. Nobody knows. The acronym is not resolved in the book where it was introduced. It is just BCE in the whole book. Nobody knows what it means. So probably there's some paper before that where they had some meaning. Quick side note, I was in a research project. We were researching autonomous vehicles. There was the logic developed which was called MET++, and nobody knows what MET means anymore. In the same software project, in the same research project that was only running 12 years, nobody could remember in the end what MET++ meant. Then referencing both of these before is hexagonal architectures by Alistair Cockburn, which was introduced 2005. Similar concepts with those I'm introducing in a minute. Then we have onion architectures. Onion architectures were introduced by Jeff Palermo, also referencing all of those before. Actually, at least one diagram I'm showing you in some minutes is originally from onion architectures. Then there were streaming architectures, Robert C. Martin, also precursor to this. And then in 2012, clean architecture was introduced. 2012 is the blog article about this. There's a book from 2017 or 2018, I don't know exactly. Basically, it is a concise form of all those above in a comprehensive form. The basic idea is to raise the solid principles for software development into architecture. Everybody knows solid principles, I presume. Okay, that's 5 or 6. 7. Okay. Solid is an acronym. It is from Design Principles and Design Patterns. That was the name of the paper. In the paper itself, the concepts were introduced in a different order, so the solid acronym wasn't apparent, but someone later on said, okay, let's call it solid because it makes solid software in the end, so seems logical. There is S stands for single responsibility principle. Every class in your system should only have one reason to change. Usually, when you implement a payment provider interface in your application, you don't keep the single responsibility principle, because usually you have some class which does your payment processing for, let's say, Visa. Then you have an internal interface. The internal interface is what your application wants to do with the interface itself. And then there is the other part, which is it is talking to Visa, MasterCard, whatever. So if either of those interfaces changes because you have to change something in your application, or Visa changes something, in both cases you have to change your class, which says, okay, there is at least 2 reasons to change this class. The trick is to use a strategy pattern in that case. So on the one hand, you have your interface keeps stable, then you have a strategy, and the strategy is exchangeable. You can put in Visa, you can put in PayPal, you can put MasterCard, you can put in whatever. If one of the sides changes, you have to change your strategy or your interface, or this one class. And you only have to do one. This leads into the open-close principle. Classes should be open to extension but closed to modification. At some point you should say, usually at the very latest point is this goes into production. At that point you should never modify this class ever again. You can achieve that. It is usually very hard to do so because you have to think about many things beforehand. For example, just the same as I just said with the payment providers, you have to think beforehand that both sides might change. Then you don't have to modify the class. You would then just have to inject another payment provider strategy that you could do probably with a configuration, but Also, you would have to think about that beforehand, but okay, you can try to achieve that. Then there's Liskov substitution principle, which is behavioral subtyping, basically, which says if you have a class A and the class A extends to class B, then wherever you can put in a B, you must also be able to put in an A without changing any contract. This is usually why squares are not, the squares don't extend rectangles in the usual programming languages, because if you have a square, if you have a rectangle, then usually your contract or your test cases are, if you change the width, the height doesn't change. If you have a square, you must do that. So either the modification must be you have to do both at the same time, or you have to say, okay, a rectangle is not really the superclass of a square. There are programming languages which can decide on which type something has depending on the contents of the class. So in those programming languages, this works. Interface segregation principle, this is basically easy to achieve. What this means is you should have very small interfaces. Small interfaces means if you have something like a printer that can also staple, that can also fold or something like that, you should not have one interface which is the super printer, which can fold your letters and staple them and print, but you have three interfaces and implement three interfaces. You have one for stapling, one for folding, and one for printing. And then we have the dependency inversion principle, which actually just means you're programming against abstractions, not concretions. You're always implementing against an interface, and some class implements this interface and can be switched in for this interface, but you're not programming against the concrete class. It is called the dependency inversion principle, because if you're taking the UML, the arrow changes the direction. So usually you have some class using some other class, then you have some dependency downwards. If you have some class, some interface, then there's the dependency, and you have the class implementing this interface, the arrow goes up. So this is why it's called dependency inversion principle. If we want to do this for architecture, there's the idea is basically the following. You have entities, global business rules, entities which have or encode the global business rules. For example, if you have a shop system, the customer always has to be 18 years old, which is not specific to the application you are writing, which might be overarching between different applications. This is in DDD, it's called sorry, it will come back. Then you have the use case, which is what your business logic is. This encodes application-specific business rules. This is what you want to write, something like you have some specific use case you want to achieve. And this might use the entities, and this might use some other things, but this is the core of your application. You encode your core functionality in this use case. Then you have interface adapters, which are adapting, connecting framework and drivers to your business rules. And then on the outside you have frameworks and drivers, depending on what you're doing. If you have IoT, then you have more like drivers. If you have, I don't know, if you have some web application, you usually have some form of MySQL or something like that. Actually, MySQL is outside here. DynamoDB is outside here. Kinesis, Mongoose, Express.js, Angular, and any form of controller is outside here. And then you have gateways, which allow you to go from the outside to the inside. And you have presenters, which allow you to present what your use case calculated to the outside. So this is, by the way, the onion architecture. You can see onion rings, I presume. So dependencies only go inside. So the outside may depend on, so the framework may depend on your interface adapter. Your interface adapter may depend on the use case. Your use case may depend on the entities, but not the other way around. This allows you to exchange a framework or a driver on the outside without the use case ever knowing about it. So if you have some change in your entities, you have a problem. Or you have a problem. You have to adapt, okay? But that should usually be rare. You have a change in your use case, not that rare, but usually slightly less often the case. Then you have the interface adapters, which have to change every time you have to change your drivers or your framework on the outside, but okay. And then the control flow goes something like this. You start on the outside, where you have a controller which wants to call a use case. So I said controllers are on the outside. I have to go over there. You have a controller which is on the outside, which is calling through some interface adapter some use case. And the use case may then have to call back to the outside to get its entities, to calculate a result, and then give it back to you through a presenter. Let's get more concrete. Usually you have some use cases. On this chart, everything to the right of the yellow line is the word of the entity. Everything between the red and the yellow line is use case, and on the outside here, I haven't got space for 2 lines, but it is either interface adapter or the framework or driver outside. And then you have a use case, and this use case needs some input to give it its parameters. What would you like to do? So you usually define a request model. There are 2 ways to do that. Either you have a class or an interface, which encodes what is the correct input to your use case, or it's just the input parameters of the method you're calling on your use case. And then the use case goes and has to get some entities from your database or something like that to calculate whatever it has to calculate. And it then generates a response. And the response, same way as the request, is some encoding of what is the result. Usually those 2 are some very simple form of DTOs. Then the use case has to give this response to an outbound. Outbound is something like your presenter. And now you have the problem, how do I get to my entities? My entities are in my database or on my S3 bucket or wherever. So the use case, or in the realm of the use case, you have a specification for an entity gateway. The entity gateway is a very concrete interface for exactly this use case, which says, okay, I give you these 2 parameters and you give me every entity that fits those. Or I give you no parameters, but you give me some form of entity. So to achieve that, and I said interface, someone has to implement this interface. And that guy is outside here. That is some entity gateway implementation which implements this interface and can be exchanged for that interface in the concrete implementation then. And this one is now specific to MySQL, DynamoDB, S3, CouchDB, whatever. Then you have on the outside some controller which must call this use case. And in the end, you have some presenter which implements this outbound. What you can see here is, as I showed you in the diagram before, all dependencies go to the right. So everything goes into the direction of this core entities. So let's just look at a very concrete example. Let's calculate the overtimes of some department. Let's assume we have, so I will show you something. Yes, I know. Quick reminder, no, I just have to say, all examples are in TypeScript. But I think that's okay for everybody. So we have this is some excerpt from my entities. These are my entities. I have some department, which has some ID, oh, I'm missing the ID, sorry. The department obviously has to have an ID. And it has employees, which are in this department, which are some string. Short examples for slides, you know. And then every employee has a timesheet which is matched to the employee ID and the start and end time for some day. You can think of more complex examples which wouldn't fit on my slide. Then you have this request model. So I define what do I want what is the request this use case gets. In TypeScript, doing this with an interface is quite useful because you get keyed named input parameters to your method. I will show you in 2 slides. And then we want to respond with overtime, which is a number. Then we have our use case. This is our business logic. If this is a very good calculation of an overtime, I don't know, but it is one. So what you can see here is we have this use case, and this use case in its constructor gets some entity gateway and some outbound, which are concrete to this use case, and then everything that is underlined references one of those 2. But I'm not saying call MySQL, call DynamoDB, call S3. In the end, generate some JSON response or something. I'm not saying that. I'm just saying, okay, with these informations, get me all departments. I have this department ID. However you give me my entities, I don't know. And then I can, from that, generate some request for the employees of this department. Then I can calculate the overtime, and in the end, I return this response. And this is with a keyed with the name parameters. You can implement an interface in TypeScript by just saying, okay, I have some object which has the concrete names in it. So this is very helpful. So this is why we usually do this with interfaces. Then we can just say, okay, quickly braces open and close. This allows optional parameters. This is order independent, and you have keyed names for your parameters. So and now we have this overtime entity gateway in the request in the slide before. We saw it has to have 2 methods: get department and get timesheet for employee, which will return the correct types. And then we can implement this. One implementation might be this. We call it the DynamoDB document client, get the item for this department ID and this table, and return it. Might be one implementation. You can go ahead and do some for MySQL or for whatever. And then you have to have an outbound. Usually we just go with some form of next and error. This allows to use an RxJS subject, for example, and just plug it in. But you can do then and catch or something, then you can do it with promises, whatever you like. And you can implement it, for example, this is API gateway response for AWS, where you can just say, okay, whatever is in the calculate response model, I know there's an overtime thingy in there, so the body of my response is this overtime. Or you can do something like on a console. And then to have a method, to have a handler for Lambda function, for example, you have this event context and callback, and then you just have to plug in the entity gateway, the API, and execute it. So let's go over testable. If we want to do tests now, we take a unit test where we implement a mock gateway, we implement a mock outbound, and then we can do unit testing. And the mock outbound just has to fulfill the interface. It does nothing. Or you can or you can put in a spy in here or whatever. Simple. For integration tests, then you would like to see, okay, it's coming in on the one hand side and then it's going out on the other side in a correct way. So you plug in some local DB entity gateway and some testing outbound. And then you can guarantee that if this test is okay, is green, then you can say, okay, my flow is working, my use case is working. If there is an error, it has either to be, if in your production environment there is an error, it has either to be in the local, in the concrete adapter for the entity gateway, or in the outbound. Cloud agnostic, we have this model, and in my implementation was API gateway in, API gateway out, DynamoDB in the middle. If I want to switch to another cloud, I would have to change this. This is basically Azure for the same use case. This would be Google. You're done. I have one thing. Usually you're selecting some cloud provider because it provides services for you that the others don't have. So cloud agnostic. If you want base station as a service, you can only use Amazon at the moment. And yes, there is a service for that on Amazon, Amazon Ground Station. You can get a base station as a service. I hope you can see that this is very maintainable. If you see this, you only know that this is something with AWS because I wrote DynamoDB and API gateway. If I switch DynamoDB entity gateway for something like HTTP REST entity gateway, then you might think, okay, this is in my front end, and it calls the back end and then does the calculation in the front end. Okay, that's it. If you have questions, I'm here tomorrow, and I can take one now, but I only have very few minutes, and obviously we're hiring. And we will hopefully release these two packages in the next few days, where at least this type magic for TypeScript is already solved for you, and you can just have to plug in these parts.
Thank you very much.
And a big applause, please.